It's a great pleasure to be here and to talk to a new audience, one that I'm not normally converse with. I'm going to apologize first. I'm going to talk primarily about the causal lens. And only 2 or 3 or 4 slides will be about explainability and interpretability, the topic that you are most interested in. But you will find the connection as I go through. You will find it, I think, throughout. Before I start, I'd like to establish some idea of your background. How many of you know graphical models? Oh, terrific. Okay, it will be easy now for all of us to talk eye to eye. So let me first start with the outline and see what we can. This is great. Here's the outline, and I'm going to first explain what I mean by causal lens. Then I'm going to talk about why causal understanding needs a new logic and a new inference engine, as opposed to the logic that we have in mathematics, and the logic that we have, and the inference engine that we normally employ to deal with mathematics. Then I'm going to talk about the 2 fundamental laws. Some people call it double helix. I don't want to be that pretentious, but it's really without these 2 fundamental laws, things do not sound like grounded. Once you have them, then everything else can be deduced mathematically from those 2 laws, and the rest is just mechanics, implementation. Then I'm going to talk about some 7 pillars, I call them, or tools for causal wisdom, some accomplishments that the causal inference enterprise can be proud of. This will include how these pillars revolutionize sciences, how they clarify social, legal, and ethical questions, and the rest of it. Okay, so let's start with the causal lens, and I'll define it. This is my lens. Okay, that's the way I look at the causal problems in life. Actually, many problems in life, because many of them have their roots in causal thinking. So this is what I mean with it. It's the assumption that there exists some unknown but true data generating process that explains the world. Every physicist would agree with me. Otherwise, a physicist will just pack and go home. But the idea that there exist some laws, I call it process. It's different than laws, and we'll see the difference in a second, that explain the data. What explain means is that you can answer questions that are of interest. And we, as Homo sapiens, have many questions about our environment. Some of them, or most of them, can be answered had we known this Santa Claus. The second premise is that the data generating process comes as a set of causal equations. I'll explain what causal equations are in a second. Those are equations that assign to every variable a value that depends on other variables, as opposed to conservation laws. Conservation laws talks about a general ensemble of things where certain properties are conserved. This is not a causal equation according to my perception. A causal is what makes a particle accelerate when there is a tide, let's say. So I say every molecule of water, when it rushes to the shoreline, experience force from the gravitational position of a moon and rushes there. That is a causal law, saying that there is a tide in a certain period of time is not a causal law. It's observation. It's regularity, but it's not a causal law. Neither is Venturi effect, for instance, okay? Which preserves the sum of the kinetic and potential energy. It doesn't explain why a particle accelerates when it goes through the constrained portion of the pipe. There is a force behind the particles from other particles that pushes it more than the forces coming from in front of it. That is a causal law, not the preservation of kinetic and potential energy. Okay, so this is my perception. The task is to infer properties of the data generating process using data and assumptions about other properties of the data generating process. It sounds like straight logic, right? You have a certain unknown Santa Claus, and you need to find some properties of it. Since you don't know anything about it, but you have some assumptions about it, and what are the assumptions? Constraints that specify some other properties of that entity. Plus you have data, and that's a great privilege and a great blessing that we do have some data in the world. Otherwise we'll be in astrology department. It's central that one of the properties that we are interested in is the consequences of pending policies or intervention on various populations and various subpopulations that are of. If you are epidemiologist, you are concerned about populations, right? If you are economist, you're also concerned about population. Okay? If you are a physicist, you're probably concerned about population of particles someplace. Okay, so this is important to know that it's not just abstract properties, like how many variables are there, or how many variables have a name that starts with T. That is a property of the data generating process, or how many variables are connected to at least 3 other neighbors. Okay? But this is not the kind of properties that we as a surviving species are interested in. We are interested in controlling the environment, and therefore one of the key properties that we'll be interested will be to predict the consequences of interventions on the environment. And who is the environment? The Santa Claus. We don't have any other perception of the environment except what the data generating process or the hypothesized data generating process tells us about the environment. This is a perception of nature. And another central thing is I will concentrate on the kind of specifications that are easily understood and easily elicited from researchers. This is a qualitative understanding of the data generating process structure. Who listens to whom? That will be the basic primitive that we'll be dealing with. Which variables listen to what other variables? Okay, now we know what my causal lens is. All my life is surrounded, revolves around this perception of life and environment and nature.
Can I ask a question?
Yeah.
The pending policies, there's some subtlety here. So like, it doesn't have to be that. It doesn't mean that I can be able to do it because I can like have causal explanations of like other things that are outside of Earth. But does it have to be something that like it seems like you could imagine things like interventions that are somehow that are possible in some sense, but you're not really sure how you could like get there.
Oh, that's a different problem.
Like
how to get there, which means
right?
I want to get food, and I don't have the policies for doing it. I don't know if I should, chase after mice or go swim and catch fishes. But I'm hungry and I want to get food. Okay, so that's another question. If you know how to predict the consequences of your pending policies, where the policy is specified by specific action you're taking, then you can generate a more sophisticated question. And how do I get there? And how do I get there means I need to have an ensemble of options.
You have to instantiate an act. Like that's the criteria for pending policies.
You have to instantiate some action. Yeah.
Action.
But it's a more sophisticated question, but it cannot be done if you don't have the question of what will happen if. Okay? Yeah. So indeed, all the optimization work that is done assumes that you know the consequences of your actions. And I'm after that consequences. Okay. I'll probably repeat the same lens later on. Okay. Out of that lens comes causal inference, which is a procedure. It's a methodology of handling the kind of problems that we saw before. It's a method of taking 3 inputs and producing answers to 2 types of causal questions. What are the inputs? What we wish to know, if consequences, that's one wish. Okay. What we do already know, and what type of data we have available to us. So the methodology requires to have 2 inputs. You need to specify them. It sounds like you're already dictating the answer. No. What I wish to know, it can be something quite complex, like the set of the sequence of action that will get me into the desired consequences. And what we do already know, in the graphical modeling case, all we know would be who listens to whom. That's a graph. Right? Or you might have some ideas of the type of functions that you have there, say linear. So you specified a linear relationship among the variables. Or log linear. Okay? These are the things that you are willing to defend on scientific grounds. And then what kind of data you have. And data comes in variety. Experimental data, okay, observational data, you have a double blindfold data and all sophisticated variations of the way you generate the data. And from what type of population, under what condition it was taken, that is also part of the specification of the data. Okay? Giving this input, you're interested in 2 kinds of outputs. And in the central concern to us will be, I repeat, effect of pending interventions, and the other one, effect of undoing past events. That will be the counterfactuals. And this is my definition of a counterfaction. There is no treatment here. Okay, counterfactuals are defined by something happened, and what if some event in the past did not take place? Undoing past event. What if my plane had arrived in time? I'm fired now. I know it. And that's important to know. I've been fired. What if my plane had arrived in time and I made it to the meeting that I was supposed to be? It's very important to realize that we make use of the consequence of the actions or the event before. I was fired. I know that it gives me information about the nature of my boss, how angry he can get when I'm late to a meeting. And that reflects back on my stipulation. Had I arrived in time, I would be still employed and enjoy life as I've done in the past 5 years. So The outputs will be questions about interventions and questions about hypothetical counterfactuals. And here are the type of instantiation of the type of questions I was talking about. How effective is a given treatment in preventing a disease? A typical intervention, questions in epidemiology. Was it the new tax break that caused the sales to go up, or our marketing campaign? I'm sure that every marketing manager would like to know that. What is the annual healthcare cost attributed to obesity? Big questions, because my friend Hernan in the epidemiology department doesn't like to talk about the cause of obesity. Obesity is not controlled directly, therefore it is not well defined. According to him, according to me, it is well defined. The cause attributed to obesity, I think it was in the New York Times in the last year, where the question was, what causes this cause, the soda or obesity? Okay. According to Hernan, you can only talk about well-defined intervention. You can control the soda consumption. You cannot control obesity directly. Okay. So, but in my world, obesity has a well-defined effects. Okay. Can hiring records prove an employer guilty of discrimination? I think that has to do with some of the issues that you are confronted with, explainability. And this is a question of mediation. To what degree we can say that, sex plays a role in the hiring process. And the fifth typical one is personal decision making. I'm about to quit my job. Will I regret it? It's a personal decision. A lot of information is contained here. I'm about to quit my job, because it tells you life was miserable for me. Okay? And will I regret it? And for people who are about to quit their job, these are the only people that you want to answer this question for. Okay? And these are a typical question, whether they are more regretful than others. Okay? And knowing my intention and knowing my tormented state of mind, okay, I would like to know if I will regret it. Okay. Now, here is the key statement. All these questions were unarticulable before the advent of causal modeling and causal inference at about 3-4 decades ago. Okay? And unarticulable in the standard grammar of science. You cannot even write it down. Try to write this down in the language of physics. Okay? Try to write even the simplest one. Given treatment to prevent it, does the treatment prevent the disease? How can you explain prevent in the language of quantum mechanics? You can compute it, but to write down the sentence, this drug prevents this disease. It's not, we don't have a mathematics for that. Now, let me go to classical physics and show you why we don't have it. In classical physics, you have relationship, symmetrical relationship between variables and other variables. For instance, the movement on the barometer is proportional to the atmospheric pressure. So assuming that y is the movement on the barometer and x is the atmospheric pressure, you express it in algebra. But algebra has a funny constraint. It's symmetric. Equality sign in algebra is a symmetric operator, a symmetric relationship, which means there is nothing to tell you here who causes whom. The atmospheric pressure causes the movement of the barometer or the other way around. Now, for us, we understand it. Every child knows that the pressure causes the movement and not the other way around. But assuming you are a robot and you are given the laws of physics in the symmetrical form, and then what will prevent the robot from trying to squeeze the barometer in order to cause rain, to bring rain tomorrow? Right? If you're just a robot and you're looking at the equations, and it's symmetric. Right? So we need to build in the asymmetry that governs our understanding of things. For computer scientists, it's not hard because we have an operator called assignment. Okay, so you take the content of one register and you assign it to another register, which is a asymmetric operator. It's not the other way around. We need to have, and together with that, we need to change the laws of algebra to accommodate this asymmetry. So you need an algebra of assignment. And this is what the graph is all about. It tells you that the value of the barometer is dictated by what nature currently sees as the value of the atmospheric pressure and not the other way around. That is the reason, the rationale for graphical models. It's an algebra for asymmetry contained in the idea of assignment, value assignment. It's different than an assignment that you find in a potential outcome school, where the assignment means controlled randomized experiment, where you put some people in the control room and some people in the smoking room, and you force some people to smoke whether they like it or not. That is the kind of assignment which you do experimentally. You can imagine that nature does that nature tells the barometer, hey, thou should move whether you want it or not, because I've just noticed a certain pressure developing in the atmosphere. If you like, if you're born under, if you're training in statistics, okay, then I noticed that statistician cannot think physics. A statistician, however, can think experiments. So imagine nature as almighty, assigns a value 2 inches to the barometer dial, okay, based on the protocol of the experiment, which is look at the pressure and then decide. That is how statisticians think. But we are physicists, right? We are commonsensical people who look at the environment and assume that nature does it. We don't have to think about the control room and the treatment room. But that's why we have an arrow. Okay. Next. If you go to the algebra, and I skipped here a lot of years of algebra, you find that the questions that you can answer naturally are organized in 3 levels. A hierarchy of levels, in the sense that you cannot answer question at level I unless you have information provided from level I or higher. So on the bottom one you have statistics, machine learning, association. Okay? The activity is seeing, observing. What if I see something, I would like to modify my belief accordingly, Bayesian rule if you want. A transition from evidence to hypothesis. The hypothesis in the form of a belief in the likelihood of other variables. This is Statistics 101, up to statistics graduate. Examples, what does the symptom tell me about a disease? What does the survey tell us about the election results? Right? From seeing to belief, from seeing to belief. Above that, you have questions that cannot be answered even if you have a Santa Claus that tells you all the beliefs in the world. Infinite data, most powerful algorithm of machine learning. You cannot answer the question of what will happen if I do, and then your question of how. Okay? How is a derivative of what if I do? If I take an aspirin, will my headache be cured? You cannot answer that if you just observe patients, some of them taking aspirin, some of them don't, some of them are cured, some of them are not. Just sitting there passively, hands back, hands out, and observing patients, you cannot answer this question. You need to have some sort of intervention, and that's why Fisher invented the randomized experiment. Okay. What if we ban cigarettes? I especially put that because whenever I come here, people tell me, what about if we do experiments, like I said in reinforcement learning? Right? But reinforcement learning only tells you and gives you an ability to predict the consequences of actions that you have seen before, that you experimented before. What if we ban cigarettes? Okay? It's an action that was never done before. Some people say it cannot be done because you can always have smugglers from Canada. But in addition to that, we can imagine and converse about the effect of what if we ban cigarettes? What will happen to the cancer rate? What will happen to the black market? What will be the price of a cigarette after we do that? We can, we may not be accurate, but we can converse. Okay? For that, you need to have intervention, or either randomized experiments, data coming from that kind of experiment, or a model. A model that will tell you, will enable you to predict it. Not directly, but in combination with data. Observational data. Now you have a combination of two things. Imagine that you have a graph that tells you what happened, who listens to whom. Plus, you have data coming from observation, purely observational data. You just look at a bunch of patients in the population. Some of them smoke, some of them don't. And then you're trying to predict the effect of intervention. That will be level 2. Beyond that, you have a level of counterfactual. That's I call imagining, retrospection, or understanding. I believe that what we call understanding is really rooted in counterfactual. Okay? Because you want to imagine how things would have been if a certain action would not have taken place or certain events did not take place. Examples are, what if I had done things differently? Was it X that caused Y? Was it X? What if X had not occurred? What if I had acted differently? Was it the aspirin that stopped my headache? Would Kennedy be alive? Oswald had not killed him? What if I had not smoked for the past 2 weeks? Thinking backward. And that's what gives us a sense of understanding. And the sense of understanding gives us the illusion that we are in control. If you keep this in mind, it will help a lot in terms of understanding. Just position yourself in the literature. You look at the paper and you say, what is it about? Counterfactual, intervention, association? It's already cut down 2/3. Once you find it, it's cut down 2/3 of your effort to understand what the paper wants to convey. It's very helpful. Yeah?
I'm trying to understand specifically the difference between 2 and 3.
The what?
It's the specific difference between 2 and 3.
Yeah.
In counterfactuals, does it sort of require like tossing out some of your data? Like, oh.
How we do it, that's a different question. What the algorithm, that produces answers to counterfactual questions, I'll show you. But
I guess I'm
Yeah.
asking the criteria for what's exactly, like, formally, what's the decision boundary between these, like, you have to classify something as intervention or a counterfactual.
if you are a question answerer or you are a classifier, you want to distinguish between this. I mean, as a reader of an article, you want to distinguish between these three levels, or as a one who needs to answer a question. But the question is whether you need to do retrospection. That is the key.
So retrospection involves throwing out data, like, right? So
Why?
Because it's like
Data, you cannot throw out data.
yeah,
You can undo events.
yeah.
That's not throwing data. The data is there. You are answering questions, so part of your algorithm is take this event that occurred 2 years ago, undo it, okay, and then produce an answer to the question. What if we hadn't raised taxes in 1985? Yeah, you see the point?
I think so. I think
You're not throwing data.
well,
Yeah, go ahead.
Throwing,
The data is there. It's a record of the United States Treasury
I mean, like rolling out
Department.
a future in which you say had like sometimes you're not intervening. So, if would Kennedy be alive if Oswald had not killed him?
Yeah.
It's like saying, say we had not like that. You know, I mean, the only access you have to the world is through your data in some sense. Had we not known or received data that Kennedy was killed,
No, we actually imagine the parade in Texas and say, imagining that Oswald's finger got stuck on a trigger.
right?
Yeah, something happened there. So we can stipulate the continuation of the scenario. Kennedy reaches his destination, he lives to the age of 95, whatever.
I just mean instantiating. Just instantiating a state that has low probability of your posterior of what you currently understand the
Correct.
state of the world. Right?
Absolutely.
That's the idea, okay.
You are violating
What you're
You are violating a known fact,
Right.
yes. But you don't throw it away,
Yeah. I mean,
because it might give you information. You know that he did kill
I
Kennedy.
didn't mean it in that sense, but I get it.
Now, from what we know, he did kill Kennedy. We know that Johnson took over, right? It's very important information to answer the question. So we don't throw data. We just go there and mechanically molest nature and undo. Yeah.
Well, this is a question you can ask, but you cannot verify, right?
But wait about verifying. You must be a machine learning person. you want to verify. I'm telling you how the mind works. Okay. Now we are going to go to implementation. And the question will be to what degree we can verify, test, okay? To what degree we depend on our assumption. All these are valid questions. But first, what we want to do, okay? And we do that, right? We do very well in all three levels. It's a good a proof that we do very well. It's was given by, what's his name? I forgot. Ernst Adams, a philosopher in Berkeley. Okay, he said, consider the following two questions. Okay, one of them: would Kennedy be alive had Oswald not killed him? The other one is. Look at the statement. If Kennedy was not killed, then somebody else would have killed him. So, we know that Kennedy is dead. Okay. The question, would he be alive if Oswald had not killed him? The other one is, would he be, if Kennedy, is it true that if he was not killed, that somebody else would have killed him? These are two different questions. They almost have the same structure, but they're different in the subjunctive mode. And his point was, we form experience. We form the consensus. Okay? If you ask it to people, 95% of them will agree to the first one and not to the second one. And somebody else must have killed him, it's fine, but would have killed him is no, no, no. Okay? So how can we form a consensus on something which is totally hypothetical? Okay? Did not care. But you and I form a consensus. A consensus is the most important criterion for philosophers. Capture the way people think and the way they converse. Okay? So the fact that we form a consensus tells you that our mind has this uniform algorithm that drives it. Otherwise, you wouldn't be able to talk. And that's what we want to capture. So that's a proof, a philosophical proof, that there is something, there is a uniformity in our mind. It wouldn't satisfy you as a machine learning person, but maybe it will satisfy you if you ask the question, should we program a robot with the same machinery that we have in our mind, which may be totally wrong, okay? But since we want to converse with a robot, perhaps we should implement this illusion or this false machinery in the robot's mind. Okay. To convince you that we have a distinct barrier between the first and the second level, I want to give you the most convincing example, and this is Simpson paradox. How many of you are familiar with Simpson paradox? Oh, wow. You must be a statistician or... Okay.
I think there are more. Or read your book.
Oh, you read my book? I have betrayed my own surprise. Okay. Okay, so this is the most convincing one that I found more convincing, that there is a definite barrier there between the first and the second. This is a typical, it could be a data coming out from observation, looking at people consuming, exercising, and the cholesterol content in the blood, okay? And you might find that this is a kind of a cloud of data that you might get, scatter plot, okay? It looks like the more you exercise, the more your cholesterol, which of course is defying our understanding of the relationship causally between the two, but that's not a problem, because we're dealing with observations here, not with the experiments, okay? And we also take data which is age-specific data. So in every age group, we see the inclination of the regression line according to our understanding of the causal relationship between the two. Indeed, the more you exercise, the less cholesterol you have in every age group. Right? But you see that the relationship between the two is simply that of aggregation. If you aggregate data, you have the line, the angle of the line, changing from negative to positive. And the question, of course, is how do you know which data to consult? Right?
I guess the question is, why do people who are older exercise more?
Say it again.
Why do people who are older exercise?
That's the whole point. It is true. People who are older may be more concerned about their cholesterol level, and they make a point of exercise. Children just don't care. It's hypothetical. Okay? But the question that is being, in every textbook, in statistic textbook, you find that Simpson paradox is brought up to show that correlation is not causation. Okay? Causation follows the negative line, our understanding of causation, and correlation gives us the wrong impression as if there is a positive correlation between the two. So ends the chapter on Simpson paradox in your textbook and saying, you see, correlation is not causation. Fine, done. But the question is that we are raising as computer scientists or cognitive scientists, why aren't we in agreement with that? Or why, if somebody tells you that we found a drug that is good for men and good for women and bad for a person, we feel uncomfortable. I'm just translating that from age-specific to sex-specific. We think binary better than we think in terms of a continuous variable like age. So imagine that somebody tells you that you found a drug which is bad for women and bad for men, but it's good for a person. Okay? You say, it cannot happen. And you're right. There is no such drug. Okay? But the question is, why do you feel an upset stomach whenever somebody tells you? There is something in your logic which resists it. And what is it? You cannot prove it in Boolean logic, predicate logic, algebra. Okay? So there's something, a new machinery that is governed by the new laws of causality that tell you such a drug cannot exist. It's against my understanding of the world. Okay? And you're right. Because according to the laws of the algebra, which I didn't show you yet, the asymmetric algebra, that cannot happen. Okay? But it shows you that there is a distinct barrier between the first level, which is correlation, and intervention. If you intervene and you conduct experiment, you can find out that indeed exercise goes down. And now the question for the practical question is, if the conclusion depends on what variables we partition the data, then there could be many variables candidates. For instance, the address of a person, okay, whether or not it's left-handed or right-handed, right? All these are possible partitions that we should consider. What guides us into saying, yes, age is something we should partition on, and which we should consult is the relevant partition and not irrelevant partition. So this is the, I did some, here we are. Okay. So we need to decide, given that, is exercise helpful or not? There are certain partitions which will give you agreement with that, and certain will give you disagreement. Which ones are good partitions? Well, some people say it's more specific, therefore it's more informative. And well, that's wrong, because I can give you a partition which will be very specific and will give you the wrong result. For instance, whether the blood pressure, which is the consequence of the exercise. So, I give you an example of a seatbelt usage. Okay? Now, this Simpson paradox has implication to the question of explainability and deep learning styles. Okay? Because if you are enslaved to correlation, it will show up in your conclusion, and a customer of your system might scream, hey, it doesn't make sense. The example is, why was my loan denied? Because you're a female. Oh, come on, and what if I were a male? It would be denied too. So who gets a loan? Those who do not divulge their gender. Okay? Okay. Now, what's wrong with that? First of all, the system is obeying meticulously the rules of correlation. Right? So the system can explain itself and say, that's the way you programmed me. I was looking at the trends, and this is what I came up with. Okay? It's a good predictor. But it doesn't make sense. But it explains why I made this decision. Okay? I was programmed to find the best predictor. And I found that the sex, if I know it, is a good predictor of denial, whatever comes with denying of alone, yeah? But if I don't have information about the sex, then the thing to do is to get the law. Okay? This comes from a correlation from Simpson paradox. So this is a kind of disagreement or unpleasant results that will come if you only deals with the system, only try to explain its reasoning. Another one is fairness. Why was my insurance canceled? Because you had traffic violation. That's reasonable, okay? What if I had no traffic violation? It would have been canceled too. But who gets insurance? New drivers with no records. It's another different manifestation of Simpson's paradox. But this does not help self-driving. It is at least fair. It is fair, but it does not help. You're concerned. Here the customer or the policymaker is concerned about the effect of this decision on society as a whole, and not about explaining the reason why the system produced that particular conclusions. Okay. This distinction that I would like to make in this form, which is very important, because most people are concerned with, not fairness, explainability, are concerned about debugging the program whenever it produced undesirable results. Okay? You need to have explanation, explainability in order to debug. What's wrong? What does it mean, debug? I mean, to correct violation of expectation produced by the system builder, not by society. Here, society is concerned with safe driving. Okay. How am I doing on time?
We normally have about 10 minutes, but yeah.
We still have 10 minutes? Okay, I'll go fast. And I'll talk about the secret of causal reasoning. And this is a distinction between doing and seeing. You've probably seen it before. Have you? How many of you have seen it before? Oh, okay, so at least 50%, I can go fast, okay? Seeing is simply following the graphical rule of Bayesian network, whereas acting requires a certain mutilation of the model. The mutilation is that if I apply my muscles to the sprinkler and turn it on, then I dislodge the influence that previously the season or the controller, automatic controller, has exerted on the sprinkler. I overcome it, I overrule it, and I subject the sprinkler to the force of my muscle, turn it on. So there is no connection here between previous influences and the current state of the sprinkler. Now I have a new graph, and I can do all my inferences on the new graph. That will give me the effect of turning the sprinkler on. Okay. So I can answer it. What if I turn the sprinkler on? What if the sprinkler were on? Okay. That already is a counterfactual. I observe something, I say, what? I see the pavement is dry, and I say, what if the sprinkler were on? Now, that's already counterfactual. It requires going backward in time, updating the prior probability of the season, and then doing the manipulation. hypothetically, and then projecting down and answering the question, then the pavement will be slippery. Okay? 3-step process. Okay? 3 steps to counterfactual. Okay? This is the fundamental law of counterfactual. It says that, look at the notation. Notation is taken from Rubin. It's saying y had x been small x. Okay? For unit u, for particular individual, particular day, particular agricultural lot. Okay? So this is a notation for counterfactual. The value of the outcome, had the treatment been small x, a specific value, is given to you. You have a model, M, mutilate the model, and calculate the value of y. Simple, isn't it? It's just predictions in a mutilated model. So there's nothing magic about counterfactual, and that's what we are doing. It's so nice, and we can talk about it. We can talk about Oswald being alive, Oswald failing on a trigger, and we can communicate, because for us, communicating with counterfactual is so easy. It's the same model of the world that we had before. All we do is a little bit of a local mutilation, and then we continue to talk. So from now on, when I say counterfactual, what is your mind going to think about? It's easy. That's what I want to, if I do nothing else in this lecture, except giving you the comfort that whenever somebody talks counterfactual, it's easy algorithmically. Okay, go ahead.
There's something that seems odd here, that you had a question of what if I had observed the sprinkler to be on?
It's different than you're at level 1. If I observe.
But that's a counterfactual. The sprinkler isn't on.
Ah, that's different.
If I had observed,
okay,
then you don't get to break the node. And,
okay.
That's different.
Yeah, but you want the difference between you as an observer and the environment? Then you have to model yourself as an agent in this environment and say, this sensor, namely your eyes, were triggered and came to conclusion that the sprinkler was on. So you put yourself in as an agent in the environment. If you want to distinguish between you and the environment, right? For me, right now, I didn't do that. I said, what if the sprinkler were on? I didn't say, what if I were to observe? Okay. But if you want to deal with the distinction between the observer and the environment, then you have to model the observer as a variable in the environment. That's separate from the actual sprinkler. You have an agent or sensor of a sprinkler, and the sensor is on. All we are is just sensors, noisy sensors. Okay, so that's fundamental law. It says counterfactual are algorithmically simple. Good. Next thing is the law of conditional independence. If you have, I'll just explain it here, it's diseparation. As most of you, 60% I saw know that. It tells you simply that if you have separation in the model, in the graph, okay, separation, then you have independence in the distribution. And that's important, because that's the mapping between the hypothetical model that you impose on nature and what you expect to see in the data. If you don't see it in the data, you know your model is wrong. So this is the source for testable implication. You can test some of the assumptions, some combination of those assumptions, not all of them, but at least you have some testable implication, which is important for discovery, model discovery, or for model evaluation, for pruning, all this. Here's an example. This is what the data generating process looks like. A collection of functions. Each variable gets its value according to what nature, after nature consults that the values of other variables. We don't know this function, that's why we call it a Santa Claus, but we know the structure. What do I mean we know? Sometimes we know, sometimes we don't know. But if you want to express your understanding of nature, that's the most rudimentary question you can ask yourself. Okay. Who listens to whom? So that's the input. And it's amazing how much juice you can get out of, I should say mileage you can get out of this qualitative understanding of nature. Combine this with data, and you have wonderful things that you can do. One is you can predict conditional independencies in the data. And that is an example of conditional independence that you need to see in the data if you have compatibility. Every missing error conveys a constraint on the data. Every missing error between two variables will be conditionally independent given the separator between the two, plus a little twist concerning colliders, so I wouldn't elaborate that. You all know it. Okay. Applications are model testing, structural learning, and reducing scientific question to symbolic calculus. And that's my next slide. Now we have an inference engine. The input to each is a query, what you want to know. Another input is the assumption, another one is data. And just explain to you in graphical form what I said earlier. 3 inputs and 3 outputs. The most important output will be an estimand. And that will be a recipe for answering the query if you had the data. Here you have. So that translates into an estimate, which actually answers the query or gives you an estimate, a noisy estimate of the query. And then you have fit indices, which tells you how variable this estimator is. Here's an example. If you have a query, what is the value of y given that I do x? Okay. And here are the assumptions. The assumptions are in the form of a graph. Where are the assumptions? The assumptions is that there is no error between y going into x. There is no error going from x to y. The absence of errors are the assumptions. From these two, the engine computes an estimand, which means translate the desired query, which has a do in it, into something you can estimate, namely expressions which involve only conditional probabilities, as if you were to see things. Comes the estimate and so on. I will go faster, and I have still 5 minutes, so I can go over the, no? Okay, these are the kind of things one can do with this algebra that comes out of the causal inference brewery. Most important things for us in this form would be to look into explanation, attributions, and susceptibility to changes. Mediation, direct and indirect effect, which have to do with discrimination and fairness and inequality and inequities, yeah. And external validity, which is generalization from one environment to another one. Every machine learning person is concerned with that, although from what I've seen, the theory of shifting environments in machine learning is not well developed, and the people who pioneer these works admit that it came to a dead end. We do not know how to handle things that we learn in one environment when the environment changes. We don't have the theory. Okay? And this offers you a theory. You pay a price for that. You have to make assumptions about the Santa Claus and the structure of the environment. Who listens to whom? Okay, I will actually stop here and leave this on the wall. Mirror, mirror on the wall. And then I can answer questions when this is displayed. Yes, Zakaria.
So, in the modern machine learning setting, when you're addressing super high dimensional data, say images, speech, something like this, we have many deployed products based on these kinds of systems, and we face questions of distribution shift. And these are settings where the raw data is something that we usually don't know how to define kind of coherent mechanical model of it. Now, like even the very basic assumptions you could make, like covariate shift or prior probability shift, map onto very kind of reductive causal assumptions, like my inputs cause my output, or my output causes my inputs. But beyond that, how do you see like making this gap between the world that we know how to specify models over and the world that we're actually deploying predictive models on?
You mentioned 2 points. First facts and then a question. The fact was that looking at distribution shift is not enough to tell you how to amortize your learning in a new environment. Do you agree on that? If you see distribution shift, the shift could have been caused for different kind of mechanism. Each of them will behoove you to act differently and to modify things differently. So just looking at the distribution shift gives you only the shift of the surface without knowing the underlying shift, what really shifted there. You cannot do that. That's actually, we can prove it. That the same distribution shift is produced by 2 different shifts in mechanism. Each one of them dictates a different repair. Okay? And if you are not aware of the shifting underneath, you are doing the wrong repair. Okay, that's the first observation. The second one is, how do we get the model? How do we get the information that is missing? And that is the Santa Claus. That is the structure of the graph. But it's amazing that all you need is the qualitative structure of the graph. You don't need the equations. And that's enough for you to dictate or to reason about the underlying shift in mechanism. That's all mathematics can deliver to you, with the proof that you cannot do better. How is the proof goes? By counterexample. If you believe you can do something without a certain information, I can show you that you cannot. 2 different models give you opposite recommendations. Okay? If you're not incorporating this needed information. So that's the proof of impossibility. Okay? That's life, which means we know what kind of information is needed, either from an expert, from a researcher that can defend those assumptions on scientific ground, or by some learning technique, namely causal discovery, that look at the data and try to infer or discover the structure of the model. There's a lot of work done recently in that area, and it should be paid attention to. And you know very well because you come from CMU, right? Okay, thank you. And more questions?
This might be something that you sort of had to hurry past because you're running out of time. But I had some questions about sort of mathematical formalism of causation. You've sort of defined, you said like instead of having A equals B, you're saying A implies B, so you have 2 sets.
No, I didn't say imply. Implies the logical connective. No. Not enough.
Okay. So I guess this is the point, right? That you're saying like that you're saying like A causes B. So you have some sets A and you have some sets of A and you have some sets of B. And it's not just any like one-way relation, but it's a specific one-way relation. I was wondering if you could say a little bit more about how
It's a functional relationship, okay?
Sorry?
The function is something we all grew up with, and we forget that the function means you look at something and you map it into another.
Yeah, but can I like, if the answer is no, the answer is no. But can I write this down using like symbolic logic, or can I write down precisely what I mean by causation?
Oh, I wrote it down precisely what I mean by causation. Why don't you accept it? I mean,
Because I don't understand, because I must have missed it. Maybe. Like if I say,
oh, here it is. Okay, let me write it down. 1 second. I know how far to go. Here it is. Here it is, okay? I have a set of functions.
oh,
Do you accept that?
yeah,
It's not symmetric, because there is something special about the left-handed argument. The left-hand argument, it should really have been an error here, okay? Nature looked at that and assigns value to that.
and what is that error?
I didn't put it here. I just said what the argument standing on the left has a special privilege. This privilege one. Okay? How do I indicate the privilege? With an arrow here. So now I look at the function, I abstract from them only the structure. Who is argument in what function? That's all I say. If you are an argument in a certain function, like for instance, R is an argument in the function of W. Okay? So I take R and I put arrow between W, from R to W. Okay? So this you accepted, right? As a mathematician.
I just don't know what the arrow is.
What do you mean?
Like, well, you're saying, well, there's like there's this privilege of the right hand to the left side.
Yeah.
And I guess I'm saying, say I had another relation, and I say like there was a privilege. How would I know that that was the same as yours?
How do we know is a different question. How we specify is what we are dealing with. Now, if you have a strong feeling, okay, that the sun causes the rooster to crow and not the other way around, if you are just in neutral, you can say, I don't know, which means there is an arrow going from rooster to sun and from sun to arrow. I can put double arrow, okay? It could be cyclic. So that's how you express your lack of knowledge, your ignorance. Everything is connected to everything else. That's a supreme level of ignorance. Okay? If you have some knowledge which allows you to cut some arrows and say, okay, the sun doesn't care about the rooster.
You show us a potential implication, it's not an actual implication.
Forget about implication. All this is classical logic. It doesn't apply here. Okay? Not apply.
Give you some wrong.
Maybe one
Yes, Sergey.
Yes, I have a kind of practical question. So, if I'm a physicist, so sometimes I deal with things like systems with the multiple order parameters.
I didn't get the last
And I
word.
deal with the systems with the multiple order parameters.
Multiple order.
So, for example, magnetization, ferroelectric parameterization, polarization, octahedral tilts. So let's assume that I want to solve a practical problem or practical question to figure out which one is more important, which one is cause, another one which one is an effect. Is that something that I can do in a more intellectual manner rather than just getting a graph where everything depends on everything and just prune it?
The only way you can separate these two hypotheses is by experiment. And the graph, if you put down the ignorance, so I put R goes into W, W goes into R. And your graph will tell you which experiment you have to do to disentangle it, to decide. So we have to separate the specification from the inference.
Since yesterday you said you were interested in the philosophy of free will, I guess my question would be, the graph itself is an abstraction for some much finer grained underlying reality. And the notion of the graph abstraction relies on there being this well-defined notion of an intervention. And I guess my question is sort of, could you imagine like, would it be consistent, could there exist a world where there would be no such thing as an intervention at the finest scales, and yet in the abstraction at which you choose to draw the graph, the causal machinery would still work, and thinking in terms of interventions would make sense?
It's a difficult question because it's self-referential. When we talk about there is really no intervention in the world, because whatever I do was dictated by my neural architecture and the noise that I receive from cosmic radiation. So what I mean to intervene? I'm part of the plasma called nature. It's not different between the intervener and the intervened. Okay. This is on the cosmic scale. But when we come to our perception of ourselves as agent in this world, and we have this illusion in our mind that we are master of our actions, okay, that makes sense. But this is all pre-programmed illusion. Okay. The question we have to answer now, how we program it. How do we program this? Once we solve the problem of how we program the illusion, then we can talk about the philosophical questions. What it means and what will happen if a robot gets free will. These are all philosophical and interesting questions. But for us, the engineering problem is to program that illusion into a robot. Can you do it? Then we can start talking about philosophical questions. But I cannot answer the question because I haven't yet programmed this illusion. It's really very interesting, and I think it's challenging to every one of us because we're all physicists.
Magicians do it in magic shows.
Say it again?
In magic shows, they program illusions. I mean, in a cabaret, if you go and there is a magician, they program illusions. Isn't that what they do?
All right. Illusions and
I bet it's a difference.
I think we should take a little bit of time for a break, and let's thank you, Dan.
Thank you.